Okay, so I would like to thank the organizers to giving me this opportunity for this nice symposium. So I'm Bunyo Hatsukade from the University of Tokyo. So today I'm going to talk about dusty galaxies in the early universe. So I have postdocs and graduate students working together in the variety of scientific fields in astronomy. We are operating the KISA Observatory in Japan, which has a 105 centimeter optical telescope. So can you see my point? Oh, no. Yeah.
Yes, we can see.
Okay, thanks. Yes. This telescope has a very wide field of view covering the wide area of the sky, so which is very useful for uncovering the very bright objects, rare objects, or to study the statistical properties of a large number of objects. So we are also operating the University of Tokyo Atacama Observatory Tower, which is in the Atacama Desert in Chile at the altitude of about 5,600 meters. So we are now constructing a new telescope operated at optical and infrared with a diameter of 6.5 meters. So we also contributing to the radio instruments or telescopes such as the ASTE or Atacama Submillimeter Telescope experiment to a large millimeter telescope in Mexico. And I'm conducting the variety of scientific fields in astronomy, but mainly working on the two topics. One is the exploration of the nature of extragalactic transients such as long duration gamma ray bursts, superluminous supernovae, or fast radio bursts. These are explained by the Hashimoto-san in the previous talk. So the nature of these extreme events are still unknown, so we are trying to understand the origins or mechanism by observing the environment to host galaxies. The other topic is the unveiling obscured activity in the early universe through far-infrared, submillimeter, or millimeter observations. So this is today's topic of my presentation. So today I'm going to talk about dusty universe. So first I will show you the multi-wavelength view of galaxies as an introduction, then explain the role of cosmic dust, which is very important to understand the formation of planets, stars, or galaxies in the universe. And there exists dust of two or more galaxies. So these are the pictures taken at optical or near-infrared wavelengths, but these objects, such as stars or galaxies in the universe, emit a wide range of electromagnetic wave. So this is a schematic view of an electromagnetic wave as a function of the wavelength or frequency. So we are usually using visible light or optical wavelengths, which has about 0.1 to 1 micrometer. At the longer side, we have infrared, far infrared, submillimeter, or millimeter, or radio wavelength. On the shorter side, we have a ultraviolet, or X-rays, or gamma rays. So these are the same physical mechanism, but have different names based on of its wavelength or frequency. But in order to understand the whole activity of the universe, we need to collect this information as much as possible. So, for example, this is a multi-wavelength view of a galaxy, Whirlpool galaxy, and nearby galaxies. So from left to right, the image taken at radio or infrared, optical, ultraviolet, and X-ray. So these different wavelengths trace different physical properties or materials. For example, in the radio band, so this figure shows the distribution of cold gas, which are the fuel for star formation, and infrared traces the cool stars and also the dust. And at optical wavelengths, we can see the distribution of stars. And the ultraviolet, we also see the distribution of stars, but it's especially for young, massive stars. And in the X-ray, we can see the very high energy events such as supernova remnant or galactic activity in the center of the galaxy. So go back to the Milky Way. This is a picture taken at the visible light. So we can see the emission from stars in the galaxy, but we also see the dark regions inside this galaxy. But if we use different wavelengths, the very completely different image emerges. So this is a composite image taken at centimeter, millimeter, and submillimeter waves. So this shows the distribution of dust and gas taken at these wavelengths. So very different materials are seen by using different wavelengths. So the cosmic dust is a very microscopic, very small grain, microscopic grain. So the size of about in the scale of 1 micrometer. So this is a very tiny object, but there is plenty of cosmic dust in the universe, so they played an important role. So they absorb optical light emitted by stars. So for example, in the right figure shows the infrared dark cloud named Barnard 68, and the central part is very dark, and there seems to be no object here, but actually the dust exists between the Earth and stars behind this cloud. So this dust absorbs the emission from stars behind this cloud. So we cannot see anything at optical or near infrared wavelengths. So dust is very important because it is a fuel for star formation. So this is a schematic picture of a life cycle of stars in the universe. And the stars are born from the molecular cloud where the molecular gas or dust are distributed, and this material of molecular gas or dust condensed and collapse into a small object, then becomes a star. And at the end of the life of a star, they will become some very heavy stars will explode and emit their materials into the space, and the smaller lighter stars also emit their materials more gradually into the space. So these scattered dust and gas are again the materials for the next generation star. So the dust are very important for the understanding of the stars or galaxies. So dust also played an important role in the understanding of the obscured activity in the universe. So this is an illustration of so we imagine that we are watching distant stars from the ground-based telescopes using a variety of wavelengths. So the stars emit the radiation at mainly UV or optical or near infrared. So we can observe the emission from stars by using the telescopes operated at these wavelengths. However, if dust exists between the stars and the observer, we cannot see the stars because dust absorbs this emission. However, the dust itself get energy from the emission from stars and then re-emit radiation at the longer wavelengths such as far infrared, submillimeter, millimeter wavelength. So by using these longer wavelengths, observatory telescopes or instruments, we can detect the emission from dust, so we can trace the existence of dust. So we can calculate the amount of dust between the stars and observers. we also understand can understand the star forming activity behind the dust, because the dust absorbs the energy and then re-emit the energy at these wavelengths. So by using these wavelengths and strength of these wavelengths, we can consider or calculate the activity behind the dust. So we can understand the dust obscured star forming activity by using these wavelengths. This figure also demonstrates the importance of observations at both optical or infrared wavelengths. So this is a figure of extragalactic background light, which is a integration of all emission outside the Milky Way. So the integration of the activity of the whole activity of the universe outside the Milky Way in this wavelength range or frequency range. So there are three peaks. One highest peak is the microwave background, which is caused by the remnant of the Big Bang. And the other two peaks are caused by the activity in the universe, such as the star or star formation or galactic activity. So these, for example, at the optical or near-infrared wavelengths, these emissions are from the stars or other activity related to stars. And the other one, so the other peak at the infrared submillimeter wavelength, it comes from the dust emission, so the dust obscured activity. So these energy are comparable in its energy. So by observing both at optical and near-infrared wavelength and also the infrared submillimeter or millimeter wavelength is essential to understand the whole activity in the universe. However, it is challenging to detect these emissions because the Earth has a thick atmosphere which absorbs emission from the universe outside the Earth. So this is a atmospheric transmission. So the wide range of electromagnetic waves are coming from the universe, but most of them are absorbed by atmosphere. Then only a very tiny fraction of the electromagnetic wave can reach the surface of the sky and can be observed at the ground by using the ground-based telescopes. And it is very difficult to detect, for example, the gamma rays, X-ray, or ultraviolet or infrared. So we need to launch a satellite to go outside the atmosphere of the Earth, or build telescopes high mountainside to reduce the effect of absorption by atmosphere. So now in the recent years, most of the state-of-the-art telescopes operated at these far infrared or submillimeter millimeter wavelengths are constructed at high mountainside. For example, this is a movie of the Atacama millimeter submillimeter array, ALMA, so which is an interferometer consisting of 66 antennas. So these 66 antennas moving at the same time and operated as one single telescope to observe deep, distant universe, and this is located in the Atacama Desert, Chile, 5,000 meter altitude. So I have visited several times these sites. For example, the left figure shows the large millimeter telescope in Mexico at the altitude of 4,600 meter, which has a 50 meter diameter dish operated at millimeter wavelength. And the right figure shows the ALMA site in Chile. So by using these very state-of-the-art instrument or telescopes, we're understanding the history of the universe. So this is a schematic view of the history of the universe. So the right-hand side shows the present day, and the left-hand side is the early universe and Big Bang in about 13.8 billion years ago. And it is thought that the first stars born about a few hundred mega year from the Big Bang, and then galaxies form, and these galaxies evolve and in history through the history of the universe, and the stars are born and die, and now eventually we are living in the present day universe with this variety of galaxies or stars. So the astronomers now want to understand the history of the cosmic star formation, which is a star forming activity in the universe as a function of the age of the universe or redshift. So this is the star formation, cosmic star formation history. So the star formation rate density, which is a star forming activity per unit volume of the universe at the time, at the age of the universe. So this figure shows different components in different colors. So one is unobscured activity traced by rest frame UV, so the observed by UV or optical or near-infrared wavelengths, and the shown in blue. And the other is the obscured activity traced by infrared or infrared or submillimeter. So this is a dust obscured activity in the universe. So we can see that the significance of the star formation in the early universe is hidden by dust, especially in the early universe, or the universe in the past about 10 billion years ago or more. So in order to understand the true star forming activity, we need to observe both unobscured and also the both obscured activity using the long wavelengths. So by using the radio telescopes, the submillimeter telescope, we have conducted the surveys of dusty galaxies. So this is an Atacama submillimeter telescope experiment, ASTE, which is also located in the Atacama Desert in Chile. So we installed ASTE bolometer camera inside this telescope and conducted deep and wide field surveys in different regions of the sky. And these are the images taken by our surveys. So we conducted surveys in different regions. So different images are shown here, but this is taken at 1 millimeter wavelength. And these bright points, so each point is indicate a galaxy, very dusty, bright galaxies in the early universe. So this is an artist's impression, but this galaxy is thought to be the very massive and heavily enshrouded by dust and actively forming stars inside the dust. So these galaxies are bright at submillimeter wavelength, so they are named submillimeter bright galaxies or SMGs. So observations of SMGs have been conducted in 2 decades, and now we are understanding the distribution, redshift distribution of SMGs. So this is one example of the distribution. So we found that the SMGs, the majority of SMGs located around here, so they're about 10 billion years to 12 billion years ago. But it is interesting that there is no such objects like SMGs in the present-day universe. So this is the stellar mass versus the star formation rate of SMGs, studied by multi-wavelength observations. SMGs are shown in the red and green dots here, and in comparison, we plot the other normal star-forming galaxies in here. So we found that SMGs are very massive and actively star-forming compared to the normal star-forming galaxies at the same time of the universe. So now ALMA is further conducting observations in detail of the SMGs. So this is the distribution of molecular gas or dust, the fuel for star formation, in a submillimeter galaxy 12 billion light years away. So we now see that plenty of molecular gas and dust exist to fuel for star formation in these submillimeter bright galaxies. So what caused this very active star formation compared to other typical star-forming galaxies? So one possibility is the inflow of large amount of gas. So for example, this is an artist's impression of this inflow of gas. So the gas is there is plenty of gas in the space, and through the cosmic wave, this gas inflowing into the center of this gravitational potential, because SMGs have a very large amount of material, including stars, or gas, or dust, or dark matter. So the gas is attracted by the gravitational potential into the galaxy located in the center of this halo system. And this is the evolution of molecular gas density as a function of the age of the universe, or redshift. So the molecular gas mass density is a molecular gas mass in a unit volume of the universe. And the left-hand side is the present-day universe, and the right-hand side is the early universe. So we are now reviewing the evolution. So the gas mass density increases from the early universe to the about 10 billion years ago, and then it decreases to the present-day universe. So it is thought that there is a peak around here, so about 10 or to 12 billion years ago. So this peak is the time is peak time coincides with the highest number density of submillimeter galaxies. So it is possible that the large amount of molecular gas fuel for star formation in SMGs. The other possibility is the merger-induced active star formation. So these are the optical or near-infrared images of SMGs 11 billion years away, and we can see that more than two components are seen in a single submillimeter galaxy, so suggesting the mergers are ongoing in this system. And galaxy mergers are not rare and often observed in the local universe. So these are a beautiful picture of galaxy interaction or merger. So the two galaxies are interacting with its gravitational potential, and then at the late phase of the galaxy mergers, and then finally collide into a single massive galaxy. And this picture is a up to 20, which is categorized as a ultra-luminous infrared galaxy, ULAR. So this is a very bright galaxy at infrared wavelengths, because a large amount of dust exists uncovering the central star-forming activity or active galactic nuclei in the area. So inside these galaxies, very active star formation occur. So this type of local galaxy is thought these bright positions show the indicate the star forming activity happens here. So this kind of galaxy merger induced very active intense star formation. And the simulations and also the observations suggest the merger rate is higher in the early universe compared to the present-day universe. So these kind of galaxy mergers are often happen in the early universe, which cause an intense star formation in the dusty galaxies in the early universe. So these SMGs are very massive and they are actively star forming, and so they are expected to be the progenitors of present-day massive elliptical galaxies. So this is a scenario for galaxy evolution. So in this scenario, the galaxy merger induced very active intense star formation and is observed as sublimited galaxy SMG, then quench the star forming activity and then evolve quiescently and then finally become an elliptical galaxy in the local universe. So now ALMA is still working very intensely to study the very more fainter objects compared to sublimited galaxies. Our group also conducted the deep and wide area surveys using ALMA. So this is an example of the survey observed at the 1.2 millimeter wavelength taken at the Good South region. So we are detecting fainter dusty galaxies in the universe. So by including these fainter objects, as well as the sublimated bright objects, these dusty galaxies in the early universe contribute more than 60% of the star forming activity in the universe 10 billion years ago. So they are very important populations to understand the true star formation history. And now ALMA also reveal very distant galaxies. So this is the left figure shows the near-infrared image taken by Hubble Space Telescope, and in the same region, ALMA observed and find objects which cannot be traced by optical observations using Hubble Space Telescope. So these populations are undetected by even with deep optical near-infrared observations, and discovered only through sublimited observations using ALMA. So it is expected that these kind of very optically faint objects exist in a very early universe, in this case about 13 billion light years away. So now we are still in the course of understanding the cosmic star formation history from the present-day universe up to the about 13 billion years ago. So again, this figure shows the two different components in different colors, obscured activity and unobscured activity. So far, optical observations can detect these higher redshift very early galaxies. So, but still unclear whether there is a obscured galaxies or how much these galaxies exist in the very early universe. So we need to observe the obscured star-forming galaxies in the very early universe by using such as ALMA. And now the JWST, the James Webb Space Telescope, has just launched last year and produced very unprecedented, deep, impressive images of the universe. And JWST is very powerful to detect much fainter objects compared to the current optical or near-infrared instruments. So JWST will provide the very different images of the galaxies in the early universe. But even with the power of this very superpower of the JWST, we also need a longer wavelength observations because heavily obscured galaxies cannot be traced even with these instruments. So the ALMA is in the course of upgrade to improve the sensitivity or angular resolution, so efficiency of observations. And the next generation radio interferometers, such as square kilometer array or NGPLA will be online in the coming decade. So the future is bright, especially for young researchers to study the star-forming activity or galaxy evolutions in the early universe. So to summarize my talk, so fine infrared millimeter observations have uncovered the existence of large number of dusty galaxies in the universe, and they play a significant role in the galaxy evolution, formation, and the cosmic star formation history. And these future high-sensitive observations at multi wavelengths will reveal the true star formation history of the universe. Thank you very much.
Okay, thank you very much for Hatsukade-san giving a very nice talk. Actually, he included a key concept to better understand the morning Toba-san and UN talks, but also he included exciting newest result about the high-Z dusty galaxies. So thank you very much. So it is time to take questions. Actually, we can ask both Hatsukade-san and my talk during this discussion time. So do you have any questions? If no, maybe I can start. Actually, I have several questions.
Mm-hmm.
So, where should I start? So, you mentioned that the sub-millimeter galaxies are not there in the local universe. So the number is suddenly decreased toward the nearby universe.
Mm-hmm.
So I forgot that figure.
Yes.
The histogram.
Mm-hmm.
I wonder if this is a real, how to say, is there any
Okay.
bias? Because, you know, for the fixed field of view, actually survey volume is very small for nearby universe. Therefore, probably survey volume is different for different. So how can we interact with this?
Oh yes, that's correct. And there is also some bias for the optical spectroscopic observations because there is some redshift range cannot be probed by the optical spectroscopic because of the atmospheric lines. So this might be might affect that around redshift 1 to 2. And also, yes, the survey volume is limited. So this is prior observations have been done with the JSMT and then followed up by the ALMA. But JSMT conducted relatively wide surveys, but is still very limited. So and also the Herschel conducted a relatively wide area surveys, and this shows some similar redshift distributions. And another bias is for example, the temperature of dust, because this is taken at the 150 micron or 1 millimeter wavelength, which trace the cold dust with a temperature of about 30 Kelvin, 20 Kelvin, 30 Kelvin, or 40 Kelvin. But if we use the shorter wavelengths, such as 500 micron, we can trace the much a higher dust temperature objects. So maybe we miss these kind of objects in this diagram. But overall, the shape is like this.
Oh, I see. Thank you very much. So basically, this redshift measurement spectroscopic redshift.
I don't remember very well, but the spectroscopic plus the photometric one.
Oh, so yeah, I just wonder if you plot the luminosity function. That's all, I think, fundamental when we discuss the number density. Actually, you can actually correct for the survey volume, right?
Yes, right.
I wonder if the luminosity function of sub-millimeter galaxies are really decreasing to the redshift 0. This one.
Yeah, like this one. So this is about 4 years ago. So now the number of objects is increasing. So this figure shows the redshift evolution of the luminosity functions. So it's not very clear in this figure, but we can see, for example, the number density is decreasing, and also this is for example, this is the ALMA followed by SMGs followed up by ALMA, and the contribution of the star to the star formation, and from redshift 3 to 3 and 1 to 2, so the contribution decreasing toward the lower redshift. So this is also the reflection of the number density of these calculations.
I see. So from high G to low G, it's decreased actually.
Yes.
Thank you very much. That's a very clear answer to me. And then Yuan has a question, so please go ahead.
So I think I have a question on this page. So it seems there's the first red point. Red star is lower than the star function rate density curves. So is there any explanation for red points?
You mean this one?
At redshift 1.5.
1.5.
Yes, it's lower than the curve. So is there any explanation for that data set?
Because this also reflects the decrease in the number density of SMGs compared to the total traveling activity in the universe. So the black curve is the history from the Mother one begins on 2014 or so, and so this is the also, so the number density decreases, and also the possibility is that we need the spectroscopic observations, the photometric observations from the redshift, and some of them are not detect optical or even in the infrared.
The area of the redshift is quite large.
Yes, so that's quite large. So because the number of the sources is still small, about 20 sources so far being. So yeah, we still have a large uncertainty in our understanding of this obscure star formation in our own observations.
So is there other ongoing AMA project that you may get more data?
Yes, yeah, there are many ALMA large programs ongoing, and I belong to one of them. So ALMA lensing cluster surveys, which target the lensing cluster fields to study the fainter objects and distant objects by using the effective gravitational lensing effect. And some of the observational results are published by our group, so the Seiji Fujimoto or some couple of papers appear. And so this data is already taken and the observations are completed. So we are working on the data.
Okay, so it might get better construction later. Thank you.
Yes, the number increases about more than 100 objects are detected in our survey in total.
Okay, thank you.
Okay, thank you for the question. Leah has a question, so please go ahead.
Hello.
Hello.
Yeah, and according to the picture, I find a phenomenon is that a white dot with blue line. I find the arrow bar gets larger when the redshift gets larger. Do we have any discussion about it so far?
This is because the number of sources is smaller in the distant universe. So the main contribution to the variable is the small number statistics. So just the difficulty in detecting and finding the galaxies in the early universe.
Okay. So it is because of far away. So there's some artificial error.
This is there are many contributions from the error, but mainly from the statistical or Poisson-like errors to this kind of a small number of statistics. So maybe very few number of sources, about several or more than around 10 sources can be used to create the point in each beam. So the error bar should be larger than the nearby one where the many more sources can be used.
Okay, thank you.
Okay, thank you for the question. Any other questions from audience, say including students or postdocs? Actually, I have more, but okay, please go ahead.
Hi.
Hi.
Sorry. I'm not sure if you talk about that. So, how we get the star formation rate density is from SMG or something?
That's a good point. I skipped this kind of background. So we are watching for example, at the 1 millimeter, this is a spectral energy distribution of a typical submillimeter galaxy. So for example, if we are able to use the many filter or many wavelength datasets, we can create a SED of the SMGs, like explained by the Toba-san's presentation. So we can fit the template to the SED to calculate the star formation rate based on a population synthesis modeling. But in our cases, most of the observations are mainly done at the submillimeter millimeter wavelength. So we just assume a typical typical shape of the star submillimeter galaxy. For example, this one. But and then using this template, we can estimate the star formation rate. So this is a spectral energy distributions from the 1 micron to millimeter radio wavelengths, and this submillimeter millimeter range traces the dust emission, as I explained in the presentation. So this peak shows the black body or gray body of the emission from dust. So we can trace the emission from dust. So we can estimate the obscure star forming activity by tracing the dust emission behind the dust. So by using this template and the model, so that's our way to estimate the star formation when we just use these one or two data.
Okay, so it's only can calculate in submillimeter or also can calculate in the wavelength. if we want to get the SFRD?
Then so if we can estimate the star formation rate, yeah, right, for each SMGs, then we count the number in this redshift bin and correct for the survey volume, and then estimate the star formation rate density for the total star formation rate coming from the subliminal galaxies in this redshift bin, corrected for the volume of the survey. Then we derive this star formation rate density at the time of the universe.
Okay. Thank you.
Okay, thank you very much. Any other questions? Actually, I have a question. To the star formation rate density. Hatsukade-san probably also showed a similar figure in 37, probably. And dust obscured red.
Yes.
Red. And then this is very interesting to me. So at the low D, actually dust obscured star formation overcomes. It's a lot. Go to the high Z, actually amount of star formation is higher for unobscured one, according to this data. But I wonder if this decline of obscured star formation at very high Z is just due to the armor sensitivity, or this.
Yeah, it is very debated. This highly debated. So whether this obscured star formation is lower compared to unobscured ones. So far, as you can see, the data points at the redshift 7 or 8 is only from the unobscured observations, so the rest frame UV observations using HST or some large telescopes, and we cannot reveal the highest redshift sources by using sublimate or hybrid wavelengths. So yeah, as you pointed out, this is because the sensitivity is limited, even with ALMA. So for example, in the ALMA deep survey in the Hubble deep field done by Dunlop et al., they did very deep observations and at the time, but they detect only massive galaxies at optical wavelengths, so they are not trace the whole of the galaxies in the same field.
I see.
Observed by the optical observations, so still the sensitivity of ALMA observations is limited. So this is one possibility to we miss the obscure star forming activity in the early universe. And this is one example of the revealing the very high redshift dusty galaxies in the universe about redshift 7 by Yamamoto-san. So this is also targeting a optical galaxies at the center of this image, but luckily they detect the very faint in the optical objects. So maybe we have missed this kind of populations in the very early universe, redshift 7 or 8. So it is still debated.
I see. So I can kind of imagine that if you go to the very high Z, so metallicity always decrease, right? Amount of dust probably also decrease. Therefore, it might be natural to see this decreasing trend of obscured star formation. I wonder if you compare the model prediction, then do we really expect that sudden decrease around 6 to 8?
Yes, there are many models which can explain this figure, and also which is opposite, because some model also predict the high obscure starting activity in the early universe.
I see.
This is because of the assumed number density of dusty objects in the early universe.
I see. So then, to answer this question, so ALMA doesn't have enough. If ALMA doesn't have enough sensitivity, then how can we make this redshift range? JWC can do this.
JWST also very useful to probe the optically faint objects in this HST observation, in the HST observations. But also, deep ALMA observations will also reveal so for example, by using the gravitational lensing effect, we can detect the fainter objects which cannot be probed by the observations in the field. But the gravitational lensing effect is affect very small area in the sky. So the problem is the area sky coverage is very limited. So detecting rare objects is difficult. So it is not easy, but we need to proceed this way. So deep observation in a wide area will reveal this kind of objects in the universe.
So does ALMA have a plan to make a higher sensitivity?
Yes, now ALMA is in the course of upgrading.
Oh yeah.
To improve the bandwidth to double the bandwidth, so we can use twice the bandwidth, so which will reduce the noise level about the square root for the continuum observations, or we can have high efficiency of line scans also.
Right.
Also, in the near future, there is a discussion to increase the number of antennas, improve this sensitivity. And also, there is a discussion to have a multi-pixel receivers to be installed in ALMA. This is still a discussing that, so not decided yet, but doubling the higher bandwidth will be done in near future, within several years from now.
I see.
Hatsukade-san, you mentioned the only massive galaxies are detected by ALMA, but I thought this figure is corrected for the mass function or luminosity function to take into account fainter object. Of course, you have to assume the faint and slope, whatever from low redshift. But if that's all true, then it's probably not just a matter of sensitivity. And if I remember, I think Fudamoto-san's example is a very good example. But if I remember, those are only few percent of the cosmic star emission rate density. So it's not going to change an order to reach an unobscure. That's my understanding. But maybe I'm not up to date on the latest research.
I agree with you that the current situation or observational results suggest that the obscure star formation in the early universe is not so high, and so Fudamoto-san's, I remember, suggestion is about 10% or so.
Okay.
Formation rate density. So that's the current situation, I think. But Fudamoto-san's example shows that there is a possibility that we have missed this kind of optically faint objects exist in the early universe. So this may be answered by, for example, the JWST deep surveys or deep ALMA observations.
That's right. Thank you.
Okay, thank you very much for the questions. Any other questions from audience? So actually, we had many questions to Hatsukade-san today. So if no, so let's thank speakers in the afternoon session. Thank you very much.
Thank you very much.
Thank you very much.
Thank you.
Thank you. And then, okay, so I think it's time to close this symposium. So let me say some small words. So thank you very much again for the participating in this first symposium at NCHU. So we really enjoyed the cutting edge astronomy. So we really hope that we can have hopefully in person the symposium, hopefully next year or next year. So let's keep in touch, and then I'm sure we will announce for the next time. Therefore, please keep pay attention to our activity for future. So thank you very much. And then I pass to Yuyen. So Yuyen, you have any comments?
Nothing special, but thanks for everyone joining this event, and hope we will see you next year on site.
Hey, so hello, Yuan. May I say some words?
Please.
Okay, thank you. I think it's beyond my expectation for the number of anticipates. We have anticipated about 26. That number is more than the people we had the symposium yesterday in Riken. NCHU joined symposium, so I think it's a very great success. I hope next time or maybe next year we have another or the second time the Astrophysics Symposium, and I also very welcome to invite Professor Hatsukade and Professor Kato. I wish next year our quarantine policy can be released, then they can come to our department of physics. So thank you and welcome. Welcome. Then, thank you. Bye bye. 谢谢各位的参加。
Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you. Bye bye.
Thank you.
Thank you, take care, Sam and Yuan.
Thank you.
It was wonderful.